All right, good afternoon, everybody. My name is Grant. Seth.
Austin.
Tyler.
Colton.
Michael.
And we are MSOE Senior Design Team OXOC. We have the tremendous pleasure of kicking off our senior design presentations today. We're so excited to hear about all of the progress that your teams have made towards your senior design projects, and we're equally excited to contribute by sharing what great strides we've made toward completing our project, NVIDIA GPU Firmware Debugging. Now, just as a little bit of a refresher for those of you who may not have been here for our fall presentation or have forgotten the last term, which is totally understandable, we're working with NVIDIA's GPU firmware team, the team responsible for developing and maintaining all the low-level software that allows your GPU to operate, especially at boot. Specifically, we're working on 3 different solutions with them. A UEFI firmware debug solution, which allows them to debug all of the firmware that allows the system to basically initialize and interact with the GPU. We're working with GPU microcode debug, which basically allows us to embed or to debug the embedded firmware that actually is running on the GPU in your system. And then we're also working on some early boot graphics, which will allow us to write to the display before the system even boots up. Now, I should say, that's what we planned to do as of last fall. However, since then, we kind of changed our direction because we realized that the UEFI firmware debug solution was far more challenging than we had thought and also far more important than the other tasks. So our new direction is to focus on UEFI firmware debug. We want to deliver a comprehensive and robust UEFI firmware debug solution to the team, specifically by the mediums of hardware debug, which means debugging UEFI firmware on actual system hardware, and emulator debug, which means debugging firmware on an emulated system. We'll dive into these more later in the presentation, but all you really need to know for now is that UEFI is the way. So I'll be handing things off here to Tyler to talk a little bit about EDK2, the build environment that we're using for our UEFI purposes.
Yeah, so to kind of begin our winter progress, we need to find a foundation to our project to start loading and building our UEFI drivers and applications. Some of the solutions out there that existed were both on Linux and Windows, and they had to do with GDB, and Pascal even had their own solution. But the one that we ended up going with was Tianacor's EDK2. This solution was just open source, had plenty of documentation, and is already what NVIDIA uses for their current build system that they are using. And here's just a quick snapshot of what a Tianacore EDK2 shell looks like. It's just running a quick EFI executable, and it's just showing that the application is running.
Yeah, now that we have our EFI development, we can talk about what our first main objective was, and that's creating an EFI application. Now, what exactly is an EFI application? An EFI application is a bootable EFI image which allows us to actually run EFI code. Now, why is that important for us to achieve our main goal? Well, an application is able to talk with different drivers to eventually see what is going on within the code. And our main goal is to talk with NVIDIA drivers so we can step through their code and see what issues might be coming from that. So we had a kind of a 3-step process in terms of our EFI application development. The first one is to create a very simple looping program just to test if debugging is actually possible. We wanted something very simple so that there's no surprises and nothing going wrong, and we know exactly what's going on in the code. Our next application is to call some of the Tianacore already made drivers to see if it's even possible to step through an EFI driver if we can. The third one is to actually call some NVIDIA's EFI drivers. Now this is our main goal. We haven't got there yet, but that is what we're trying to strive to do. Now I'm going to pass it over to Michael to talk a little bit more about EFI drivers.
Yeah, so as Colton said, our EFI application needs to make calls to different types of drivers. So what exactly do these drivers do? Well, they produce protocols, which protocols are basically like libraries that the application can call to and accomplish things within the system during the boot process. So initially we had planned to develop our own EFI driver, but we kind of ran into some issues with that. We found that building an empty driver template was pretty easy, but actually adding protocols and debuggable functionality was difficult. We spent a lot of time as a team trying to figure out how to develop an EFI driver, and it ultimately used up a lot of our time. So we decided to switch over to using pre-existing drivers that exist within the Tiana Core EDK2 framework, so that way we could focus more on debugging and less on the EFI driver development. So I'm going to pass things off to Tyler to talk about hardware debugging. Yeah, so after we had gotten our applications and drivers figured out, and we were moving into actually how are we going to step through the UEFI code that we wanted. So as Grant mentioned, some of the ways we decided were emulation and hardware. Through hardware, we had decided to go with third-party UEFI debugging. So through hardware debugging, we decided that third party was an existing technology was the best way, as it just provided, it was going to be out of scope for us to develop something of our own, and would have been a senior design project in itself. So we decided to outsource to these 4 companies that we were able to find, Inside, AMI, Intel, and Lauterbach. We broke them up by using a solution matrix to just compare different costs, compatibilities, and functionalities. And from that, we were able to decide that Intel was going to be our best choice. They were their development kit was free, it had plenty of documentation, and it just had the most functionality that we were looking for. But this is still something we're in the midst of developing, and we have run into some computer hardware limitations, but Michael can talk a little bit more about that.
Yeah, so we decided to go with Intel System Bring Up Toolkit, and this requires a technology called Direct Connect Interface, or DCI. Basically, DCI is a debug interface that works with, or that's supported by Intel hardware that essentially allows us to debug a target system via a physical USB connection. So this allows us to do things like step through source code that's being executed by the CPU and view and change the contents of memory. However, we've run into some issues with using DCI. Specifically, we've struggled to find hardware that actually supports this technology. We haven't so much struggled with finding CPUs that support it. The main issue comes with motherboards. The reason for this is because DCI actually poses somewhat of a security risk because it allows you to see what's being executed on the CPU and also allows you to view memory. It's because of this that motherboard manufacturers generally disable this option and don't allow the end user to use it. So our solution moving forward for this is we are actually going to hardware hack a motherboard. Specifically, there's an ASRock motherboard that there are multiple guides on where you can change the settings in memory to re-enable DCI. So moving forward, that's what we're going to do so that we can use DCI and eventually achieve hardware debug. I'm going to pass things off to Austin to talk about our emulated hardware.
Thanks, Michael. So one key decision our team had made throughout this quarter is that in addition to our hardware solution, we wanted to pursue a solution to UEFI debug through using an emulator, which is essentially a virtual machine for a UEFI shell. So the main reasons that we decided to do this is that one, it is more widely available, so employees at NVIDIA could have the emulator on their own personal workstations as opposed to needing to reserve a third-party system, which may be limited. And while there are several use cases where using the hardware as opposed to an emulator is necessary for debug, such as certain behaviors of the NVIDIA driver or GPU on boot, an emulator will suffice in most cases. So regarding the environment, there are 4 main tools that you need. This will be your emulator itself, a compiler, a debugger, and of course your EFI development library. So for the emulator, we decided to go with the Primeau emulator. This is because it is the most widely documented emulator we could find, and it also has tools that works really well in conjunction with the Tiana Core library, which of course is what NVIDIA uses. So if you're on Linux, it uses GCC as the compiler and GDB as the debugger. And if you're on Windows, it will use Visual Studio as your compiler and WinDebug as your debugger. So within the Tiana Core EDK library itself, in addition to the UEFI application or driver that you wish to debug, you will also need to build that driver application within what is called the OVMF emulation package. And this stands for Open Virtual Machine Firmware. And what this allows you to do is it will generate a binary image with your application or driver preloaded onto it that the emulator can then boot off of for you to be able to step through and see your code. So before I pass things off to Seth, I'm going to go through the basic steps to how to achieve step-through debug using an emulator. The first step is to set up your environment. So these are the tools I went on the previous slide. The next step is to build your OBMF binary image with your application or driver loaded onto it. You then run the emulator with that generated image. You attach your debugger. So if you're on Linux, this would be GDB. And lastly, within the debugger, you import your debug symbols, you set a breakpoint, you run your application in the emulator, and now you can see through and step through code. So since our end goal is to step through the NVIDIA driver, one final step, additional step for that is, because it is a virtual machine, and the driver can the GPU, we will also need to enable what is called hardware pass-through, which allows the virtual machine to communicate with the PCI lanes on the system. Now I will pass things over to Seth to go through our demonstration.
Yeah, so it's awesome to walk through those first steps are really setting up our environment. And then after that, we can build and run our emulator. So I'll walk you guys through that process right here. We got our emulator booting. You can see the Primeau emulator, Tianacore logo, and we get into our shell here. So then once we get into here, it allows us to run our custom programs that we compile. This is our simple loop that you might saw earlier on one of the slides. And one of the key things that's going on here that you can't see is that the emulator itself is outputting all the memory locations and everything that's accessing to a debug file in the background. We're then able to use that debug file, scrape for it, as you saw us ran a script, and find all those locations in memory. And that's what allows us to link the source code that we have with all of those compiled binaries and find out exactly where those are in memory and step through that code. So once we run that in our debugger here, we're running GDB. We ran the script that has all those locations, set our architecture to the correct CPU so it knows where exactly to find them, and then we can connect through a virtualized LAN port to the emulator. And you'll notice on the top where it says Kimu, it'll say stopped, as the debugger is now taking control of the emulator CPU or clock here, and it's able to control it. We can then set our breakpoint, any location, so right now this is the name of a function that we have compiled, and it will set it there. You can also put in a file and the line number of the source code that you want. Once we type continue or C, the emulator will then continue in a free run mode until it hits a breakpoint, of which we can run our program, hit that breakpoint, and you can see now we're stepping through code. And as we walk through this, it'll go into that function right there, that's our loop, and it can continue to press S, which just step into, and it'll keep stepping through code. So one of the key things with this, our next step is to communicate with the NVIDIA driver. I hope through this demonstration you can kind of understand how that might work. NVIDIA, the driver is going to work kind of like a library that's ran by our application that we can then step into that driver and see what exactly is being executed. And that will allow us to communicate back and forth and allow NVIDIA to test that driver fully. So a couple things, key points that we really noticed throughout this process are a few different things. Well, UEFI itself is fairly new technology. It was only documented or standardized about 15 years ago. So it's kind of hard to find the documentation fully for this Tianacore library and all that kind of thing. It's open source code, but a lot of the communication is closed source or behind walls, so we can't access it fully, which leads to a large learning curve. Through our senior design project like this, it's hard to become a subject matter expert on everything. So we have to lean on each other for our various different experiences to get through and try to figure out how to get around different blockings that we have throughout the process. And finally, we got through this entire process both in Windows and Linux. If you haven't noticed, we're running in Linux here. The reason for that is just that GPU pass-through, the next step that we need to achieve, is fairly difficult in Windows. It's not very well documented, and you'll notice online that people are trying. They're running into issues, and most people say it's theoretically possible, but they've never got it working themselves. In Linux, it's a documented process often used for gaming and that kind of thing, and that allows us to continue fairly easily, and that's why we'll use Linux moving forward. So, as you guys can tell, we've had the opportunity to work on quite a few things over the winter term, but that doesn't mean our project is done yet. Here's some of the goals that we have for our spring term. We of course want to continue our work on both our hardware and emulated UEFI debugging solutions. In the hardware realm, we want to continue to explore and test the solutions that we've already picked out. We haven't had much of an opportunity to do that yet because of the hardware issues that Michael discussed earlier. Once we have them up and running, we want to compare it with our emulated solution that we currently have running to see which applications it fits best. Maybe it's better at one thing than another, or maybe it's worse, and that allows us to judge how we can distribute it to NVIDIA. Of course, then we want to package it, document it, and deliver it off to the GPU firmware team. With our emulated UEFI debug solution, We want to continue to reduce, refine, and robustify the work that we've done so far. That way we have a nice, streamlined product that works from end to end, that of course can also be packaged, documented, and delivered to the GPU firmware team for internal deployment. So as we move forward, we're going to deliver a really awesome UEFI debugging solution to the GPU firmware team at the end of this spring term. Hopefully we'll have a really awesome presentation for you when that swings around with some really cool examples. But until then, thank you all for attending, and we'd love to answer all of your questions.
If you have any questions, you can either walk up to the mics here for the stream, or we'll repeat them for you if you want to yell them out.
Yeah, what's up?
Do you anticipate any risks moving forward with your plan for quarter three?
Sorry, could you repeat
Do you
that?
anticipate any risks going into quarter three, and how would you kind of like hold out with that?
Yeah, so the question was, do we expect any risks going into quarter three, and are there any ways that we can, work around those? I think the biggest risk for us is going to be the unknown, because there's a lot of UEFI challenges that have popped up already that we could not have foreseen with our experience. So I think the biggest risk is our own inexperience with UEFI. I think the best way to mitigate that is to, keep our eyes on the prize, keep moving forward, keep making sure, we're reading the documentation thoroughly and understanding things before we move on. And even reaching out and asking contacts that we know are, a little bit more familiar with the stuff that we're working on. But if anybody else have anything they'd like to contribute?
Yeah, I think some of the problems that we ran into this quarter is not that we weren't unable to do stuff, we weren't skilled enough to figure it out, but rather that we just don't have the time fully to do some of that things. It'll take a full day in documentation trying to process everything, and as a senior design project, we sometimes don't have that. So that might be a risk moving forward. We might be in over our heads on some of those kind of things, but yeah.
Any other questions? Okay, thank you.
Thank you. Thank you guys.